All right, everyone, this is the second part of section 8.2. We're basically going to do the same thing we did in section at the beginning, except it's going to be formal now. Like we're going to put a whole entire hypothesis test together, language, terminology, everything else. Okay, so you're going to see one general example and then one specific example, and then hopefully that's enough. I apologize in advance. This one might take a little longer than some other ones. We'll see. Anyway, so here's the formal language for a test of significance. The first thing you do, and we're going to number these actually, is you name the test. So you must name the test. Okay, this is called a 1 proportion z test. That's the name of this test. There are other tests that we're going to do. So the first thing you do is you name it, and then you check the conditions. So the conditions are the exact same conditions as they were for the confidence interval, except for we use P naught and Q naught instead of P hat and Q hat, because we're starting before we do that, basically. So the conditions are simple random sample, and P naught and Q naught greater than or equal to 10, and the population at least 10 times the sample size. So you would list those, verify them before we start, because we're using a normal curve, remember, to do this. So we have to make sure everything's normal. Second thing you do is you state your hypothesis in words. And then typically after we say it in words once, we define symbols for them, kind of like a word problem in algebra. So we know what they mean. You got to say it in words first, but then you can use the symbols afterwards. So our null hypothesis is going to be something like P naught equals something, right? So the percentage of success is P in the population is P naught. That's very vague. It would be something like P naught equals 0.3 or 0.4, but P naught would have some meaning. So like you'd have to say the percentage of people who did their homework over Thanksgiving break is 40%. Okay. So you need the words, basically. So that's just generalizing there. We always have an alternate hypothesis, okay? Because remember the idea is we're going to check this null hypothesis. Yeah, it's called a null hypothesis, by the way. I don't know if I said that. Null hypothesis H sub 0. Then there's an alternate hypothesis H sub A. The alternate hypothesis would be what happens if we reject our null hypothesis? What do we believe? So the alternate hypothesis can actually be one of 3 different hypotheses. The one we've done so far, the one we did yesterday, was P does not equal P naught. So we said like P naught equals 0.4. P naught would be not equal to 0.4. You could also do greater than or less than also. For now, we're going to stick with 1. Tomorrow's lesson or the next lesson is actually how you do the greater than or less than. That might be important if we want to test to see if it's greater than or less than. All right, so the third thing we do is find that test statistic, right? So we do a little math. We compare it to a critical value, which is predetermined, Z star. Could be 1.96, could be 2.575, could be anything really. And then at this step, we're also going to find a p-value, but we're going to do that later. That's why I changed the color. That's in the next lesson. We're going to skip that now because otherwise it just gets way too long. So remember, we did this yesterday. This is how you find the test statistic. Whoops. Should be a Q naught here. P naught, P hat minus P naught over P naught Q naught over N. So we find that test statistic. You should always draw a picture, and on that picture, you put your Z stars, the 1.96s or whatever they happen to be, because these are going to dictate what are called rejection regions, right? If they're out here, rejection regions, if they're out here, those are statistically significant events, which means we're going to reject the null hypothesis. They're in the rejection region. So the fourth and last and maybe most important thing is we got to come up with a conclusion. So either you reject the null hypothesis. If you're out in that rejection region, you reject the null hypothesis, and I'll show you the wording on that in just a second. So you'd say, I reject the null hypothesis. I accept that the alternate hypothesis is true. However, if it's not statistically significant, then we fail to reject the null hypothesis. Notice I did not accept. We do not accept it. We just fail to reject it. Okay, and I'll show you the wording on that when we did. And then what does that conclusion mean in the context? So we put the contextual words in there. And when we go through a walk like we're going to right now, I'll show you what that all means. So here we go. This is now a specific example. I'm going to walk through the same exact things. These are everything you see me write down here is what I would expect to see on a hypothesis test. So we're going to do the same one we did before, just to not confuse you. We're going to do that one where we spin a coin 40 times, we get 17 heads. The hypothesis is that it's 50%. But this doesn't have to be heads or tails or coins. It could just be, I believe the proportion of successes in the population is 50%. I take a sample, I get 17 out of 40. Then we test that, right? So first thing, I didn't even name the test. Silly me. So number one would be one proportion z-test. And then you list the conditions. You would not actually write that, right? Simple random sample. Yes, I'm telling you it's a simple random sample. NP naught is 40 times 0.5 is 20. I didn't write this down, but I guess I should. And Q naught is 40 times 0.5. It's also 20, both greater than or equal to 10. And the population is greater than 10 times the sample size or greater than 400. Got to write those out. You have to tell me what those numbers are. Can't just say the population is greater than 400. That doesn't mean anything. That's not a condition. It's not the condition is the population is greater than 400. The condition is the population is greater than 10 times the sample size. Oh, there, I did name it. It's a one proportion z-test. All right. Null hypothesis in words first, right? The proportion of heads when a penny is spun is 50%. Whatever the context is, you give it, and then you can use those symbols, P naught equals 0.5, and you can use those symbols until the end, so you don't have to keep repeating. The alternate hypothesis, is P naught does not equal 0.5. You could write P. Sometimes you get confused. Sometimes we write P equals 0.5. P does not. It doesn't really matter. P is the population. P naught is our guess, so it's better to say it's a guess, but it's more formality than anything else. So our hypothesis, null hypothesis, is that it's equal to 0.5. Our alternate is that it's not equal to 0.5. Third thing you do is you find a test statistic. So the test statistic is what we got, P hat, 0.425, 17 out of 40, minus 0.5. Over 0.5 times 0.5 divided by 40, it's negative 0.95. What does that mean? Well, I got a little picture here. Notice my picture has the critical values. Nowhere in the problem did it say what the critical value is, right? So if they don't tell you, it's always 95%. I mentioned that yesterday. So notice that negative 0.95 is not in the rejection region. Okay, it's called critical regions or rejection regions. The p-values for later, again, right here. We're going to find a p-value later, okay? So it's not in the critical region or rejection region. Sometimes we interchange those words, all right? Rejection region. Therefore, it's not statistically significant. So we failed to reject the null hypothesis. If we had rejected the null hypothesis, we would have said there is evidence that the proportion of heads is not 50%. We would say there's evidence of the alternate hypothesis, okay? But we didn't. So we can't accept it. So all we do is say is very simply, there is not enough evidence to reject the hypothesis that the proportion of heads is 50%. Okay. So final conclusion is always a statement about, here's very important here, the alternate hypothesis. Always. So either you reject the null hypothesis and then you say there is evidence of the alternate, or you fail to reject it and you say there's no evidence of the alternate. So for this particular problem, we would say there is no evidence that the proportion of heads is not 50%. Notice back here, the alternate hypothesis is the proportion is not 50%. When you're done, you're either going to say there's evidence that the proportion of heads is 50%. No, sorry, let me try that again. There is evidence that the proportion of heads is not 50%. If you reject the null hypothesis, you accept the alternate. If you fail to reject the null hypothesis, then you just say there is no evidence of the alternate hypothesis. So notice my wording. There is no evidence that the proportion of heads is not 50%. If you rejected the null hypothesis, you would just take out that word no. It would just say there is evidence that the proportion of heads is not 50%. Those are the only two possible final conclusions in a hypothesis test, all right? It's always about the alternate hypothesis. All right. So we'll do a couple more examples in class. There's a couple other things here. Thing number one is types of error. We might make a mistake, right? We don't know. The problem is we're never going to know. On the head flipping the coin problem, of course we know. But in the real world, we're not going to know the population proportion. So we don't know. We could make an error. So there are two types of errors. I'm going to actually kind of compare real quickly the two types of errors. It's the same basic errors you might see in a jury trial, actually. If you think about a jury trial, in a jury trial, the defendant is either innocent or guilty, all right? And then the jury, sorry about that, can't see it, the jury decides either not guilty or guilty. The jury never knows at the end whether they're right or wrong. They hope they're right? So if the defendant, sorry about that. If the defendant is innocent and they said not guilty, they got it right. Hey, awesome. But if the defendant was guilty and they said not guilty, they made an error. And then if the defendant is innocent and they said he was guilty, they made another error. And if the defendant was guilty and they said guilty, they got it right. Okay, so there's four possible outcomes, just like our hypothesis. I put worse error. One of the things that's kind of like our errors in these tests too, it's open to interpretation which error is worse. Some people might think, I might even ask you this in class just for your opinion, that the guilty person going free is a worse error than an innocent person being in jail, or vice versa, right? Some people might think the opposite. Depending on which way you think, if you're sitting in a jury, your standards are going to be different. If I'm sitting next to you and I don't want a guilty person to go free, but you don't want an innocent person to be in jail, you're going to think differently about the evidence than I am. Like your standard's going to be different, right? I don't want a guilty person to be set free, which means I don't need much evidence. Oh, hey, someone thought it was you? Yeah, you're gone. But you don't want the innocent person in jail, so that little evidence is not good for you. You need more evidence, right? So it just depends. It's the same thing in a test. So either the null hypothesis is true or false, but we're not going to know. We came up with some decision. We either rejected the null hypothesis. So remember, if the null hypothesis is true, and we don't reject it, we got it right. Awesome. But if the null hypothesis was true and we rejected it, we made what's called a type 1 error. Type 1 error is rejecting a true null. Okay. But if the null hypothesis was false and we didn't reject it, we should have rejected it, right? Rejecting it is the right answer, but failing to reject it is another error. This is called a type 2 error. Failing to reject false null. Again, we're not going to know, just like the jury trial, we're not going to know whether we got it right or wrong. We're just going to hedge our bets. Now, depending on what we're testing, if this were like a company or something like that, we might think a type 1 error is worse than a type 2 error, or a type 2 error is worse than a type 1 error, just depending on what we're doing in our company. Like we don't want to reject a true null, so we make sure we don't reject it. So your standards become different. You could change your critical values, right? You can take a bigger sample size. You can do things. All right, so this is just a couple little things. If you get a large z-score, we're going to reject the null, right? But it's possible that null hypothesis was really true when you rejected it. So one of three things happens when you get a large z-score. Either you rejected a true null, which means you got a rare event, which is going to happen, by the way, if you do 95%, it's going to happen 5% of the time. That's one thing that could happen. The other thing that could happen is the null hypothesis wasn't true in the first place, which is great. We got exactly what we want, okay? Or there's always a possibility you did something wrong, but we're going to kind of ignore that. We're going to assume we did everything right. So if you get that large test statistic, that large Z, you're going to reject the null hypothesis. So it's possible you make a type 1 error. You can't make a type 2 error if you reject, because remember, making a type 2 error is failing to reject a false null. So if you reject a null, you might make a type 1 error. And then on the other side, if you get a small test statistic, you might not get it, right? So if you get a small z, if you get a small z, sorry, if you get a small z, you fail to reject. So one of three things could happen again. Maybe the null hypothesis was true and you failed to reject it. Perfect. That's what you want to happen. Maybe the null hypothesis was false, though, and you should have rejected it. Okay, but it was just a rare chance that those two numbers were close, which is going to happen. You're going to make mistakes. Or again, it could have been biased, right? So you could be making a type 2 error in this case if you failed to reject. You can manipulate this at the beginning. Remember that we have rejection regions, right? You get to determine how big those rejection regions are by picking alpha, right? If you make them really small, it's harder to reject, right? You're more likely to fail to reject. Fail to reject, right? So you get to decide this at the beginning. So let's say you don't want to make a type 2 error. That's the one you don't want to make. Okay. So you want to change your significance level, right? So there's ways to manipulate. The idea here, though, is if you want to avoid a certain error, you increase the chances of the other one, right? So like if you want to not make a type, so remember a type 1 error is rejecting true null. So let's say you don't want to reject a true null. So how do you avoid rejecting? Well, you get small rejection regions, right? But if you have small rejection regions, you have bigger fail to reject regions. So there's more likely you're going to fail to reject, which could mean you're making a type 2 error. So they are connected, just like the jury trial is connected, right? All right. And then two last little things. If the null hypothesis is really true, we're still going to reject it sometimes, right? Because we're going to get a rare event. So if the null hypothesis is true, the probability of making a type 1 error is actually equal to whatever your level of significance is. If your level of significance is 5%, you're going to make a type 1 error 5% of the time. It's just going to happen because you're going to get a rare event, okay? And the last little definition is the power test. We'll talk a lot more about this one later. I'm just going to give you the definition right now. The power of a test is the probability of rejecting the null hypothesis, not whether it's true or false. Notice up here, it's rejecting a true null hypothesis, right? So the power of a test is the probability of rejecting the null hypothesis. So you just need to know what that means right now as a definition, and then we'll talk more about that later. Sorry, this one was a little longer, I think. I don't have my watch on to know, but I felt a little longer. One more part of section 8.2 to finish up on Friday. So we'll go over some of these in class.